Hiya. So in this video, we're going to be talking about the normal distribution. So the normal distribution we've actually kind of seen before, right? This was when we were looking at an approximation for the binomial distribution. So all this is technically is just that. So we just take the normal distribution. So the standard normal distribution is a distribution where we let our f of x, so in this case we use phi of z because it's fairly normal. This is what we were using beforehand, so I'll just stick with that notation. This is equal to 1 over the square root of 2 pi e to the minus 1 half z squared. So this is what the density function is for this. Now remember, taking the integral for this function is actually notoriously hard. I don't expect you to do this. So normally when we're talking about normal distribution, we'll still keep using the approximations, like the big phi that we had. But for us, I'll give you a couple of the approximation, or a couple of the solutions to a couple of the formulas that we should know. So the first one we should know right off the bat is that if I take the integral of everything, well, the area under the curve has to be 1. So this is just the probability of everything. The expected value, so this is expected value. Expected value of, I guess we'll say, well, I guess I do it up here. So expected value of z. So this is just 0. And if I do z squared, then I get 1 back. So what this basically is saying is we have the following thing. So if I have z be the standard normal random variable, so it's coming from a standard normal distribution, then the expected value of z and the variance of z are equal to 0 and 1 respectively. But obviously, if you kind of recall what we did in the last video, we were able to scale and alter our continuous into standard continuous. And we can do the same thing with normal. We can take our standard and move it to normal distribution. And we already actually technically have seen this, right? This formula is fairly well known. And so the normal way the way to get normal from this is just to look at this formula, right? Where x is going to be my normal version. So here, let me see, my x, z is standard normal. And x is normal. And if we let z equal to x minus mu, mu being the expected value or whatever, and sigma being the standard deviation, then we end up getting with this, we get this formula. And then looking at this in our formula, like how do we plug this in? Well, the density function was basically, we just said it's equal to this thing, right? This is the density function. I guess I should highlight it with this. This is the density function for x. Probability density function for x, right? And this you can very clearly see the kind of things we had before, right? So we have 1 over sigma times square root of 2 pi. So this 1 over sigma is basically helping us keep the area under the curve 1. And then we just plug in x minus mu over sigma. So x minus mu over sigma, that becomes squared, etc. And so that's the density function for our normal distribution. So the expected value for this one, this shouldn't come as a surprise, but we can just use the same formulas as before. So if I look at x, x is equal to mu plus sigma z, right? So this is just looking at things backwards, right? So if I just take this and move things around, so this is just mu plus sigma e of z. Well, e of z is just 0. So we get mu, which is exactly what we would expect. We expect the expected value of a normal distribution to be mu. This is where this came from. And the variance, well, what's the variance? We get mu plus sigma z, remember the mu kind of gets canceled and we get a sigma squared in front. And we get var of z. Well, var of z we also know it's equal to 1. So this is just sigma squared. And this is where the standard deviation comes in. So standard deviation of x is equal to square root of sigma squared, which is equal to sigma. And that is why we call the mu the expected value and sigma the standard or sigma the standard deviation. This is where this terminology is coming from, because this is literally where it's coming from. Now, the normal distribution actually has a second name to it. And so sometimes this distribution is called the Gaussian distribution. So if you've ever seen Gaussian distribution, that's one thing that kind of gets shown occasionally, or the terminology that gets used. I'll usually use normal, but just note that in real world, normal and Gaussian both are the same thing and they both get used interchangeably. So what I want to do next is actually look at what this distribution looks like, what the density function looks like. Because I think we've talked about this quite a few times, but I think people haven't really seen or even tried to experiment with this. So I kind of want to see what this looks like. So here I have my function. So this is, maybe again, it's a little hard to see. I'm not 100% positive. But this is my phi of z. And I've given myself the ability to alter my mu in my sigma. So if you can, you should try this on Desmos, or the application I use is called GeoGebra. So I highly recommend you trying this. But what you can do is you can, so here, like, let's see what happens when I alter mu. So if I change mu, mu is the expected value, and you can kind of see that all it does is it just moves where the height is, right? So since the height is changing, we can kind of see where everything is. So it's just changing where it is. So it lets me move left and right. Standard deviation, on the other hand, is basically keeping track of how close everything is to one another. So as I increase sigma, everything gets spread apart. And as I decrease sigma, everything comes closer together. And you can see it starts spiking when I get closer and closer. Can I get this even smaller? Yeah. So that's what sigma is doing. Sigma is pulling things up, seeing the variation, and then mu is moving things back and forth. So what we'll do is so like I said, one of the things we're going to do is we're not going to look at this integral. We're just going to use the phi approximations, just like we learned in the first couple weeks. So don't worry about calculating this integral. And then we'll look at an example of this in the next video. So I will see you then.